Hello students, my name is Shashank Shekhar and today is the sixth lecture of the chapter Aldehyde Ketone and Carboxylic Acid. So if you look at the syllabus here, so we have covered aldehyde and ketone whole and today we will go to carboxylic acid part. In the last class we have seen aldol reaction, majorly aldol reaction and Cannizzaro reaction. Also we have seen the mechanism of Clemmensen reduction and Wolff-Kishner reduction. So if you remember the previous class, in the aldol reaction, the definition was like that if we take a 2 moles of a carbonyl compound, that would be aldehyde or ketone, and treat it with dilute NaOH or in the presence of any dilute base, then it would result in a alpha hydroxy ketone. Okay. Now if you further heat it, then it will result in the dehydration of the beta hydroxy ketone, and that would create alpha beta unsaturated ketone or aldehyde. So this was the basic definition of an aldol condensation. Now we have also seen that if there was absence of this alpha hydrogen, then that would result in say this Cannizzaro reaction, which is the disproportionation reaction. But one condition has to be changed there, that first of all no alpha hydrogen, and second that the base or acid we are taking must be concentrated one. So this was Cannizzaro reaction, and in that reaction 2 moles were again used, but now one was converted into say oxidized form, that is carboxylic acid of your carbonyl compound, and another into alcohol. So in this reaction both oxidation and reduction reaction was taking place simultaneously, so it was a disproportionation reaction. So today we will see carboxylic acid. Talking about the nomenclature, we will not go deep into the nomenclature. We have already seen the nomenclature of aldehyde and ketone, that would be similar to it, only the this is suffix. Okay, the suffix will be changed and would be IC. Next we will see the acidic nature tomorrow. Today we will basically focus on this methods of preparation. So if you talk about the today's topic, so first we will see the name of some common carboxylic acid. So I have put up this slide because in many questions you may be given the names, common names basically, of some common carboxylic acid that is also important for our daily life, and some of this are part of our body functioning also. Then we will move to the structure of carbonyl compound. So here also I have discussed briefly about the structure, because the structure is very important both for the preparation and mostly for the chemical reactivity of a given chemical compound. Next we will see some methods of preparation, starting from alcohols and aldehydes through oxidation. After that, from alkyl benzenes. Alkyl benzenes are basically that aryl benzene, I would say. Sorry for this. Sorry, alkyl benzene. Yeah, right, clear. Alkyl benzene means benzene is connected to a alkyl group. Then from nitrile and amides. So if you are not aware about the structure, no problem, we will see it. Then we will see how the mechanism goes for the creation of this carboxylic acid from amides. So basically they are hydrolyzed. So we will see the mechanism of that hydrolysis. Then we will see how can we do the same from ester, and after that from the Grignard reagent. So these are today's topic. So let us start our today's class. So first of all, let us see the list of the carboxylic acid that we will focus on. So starting from the first smallest group or the primitive group of this carboxylic acid family is called formic acid. So it is similar to the formaldehyde. So you must have seen the formaldehyde. It was in this fashion. This is formaldehyde. Now similar to that we have one carbon only, and it is the smallest member of the carboxylic acid group, that is formic acid. Next, similar to acetaldehyde, we have acetic acid. Now if you look at the corresponding IUPAC name, so since one carbon is present, so methanoic acid, 2 carbons, ethanoic acid. After that, if you have 3 carbon, we know it the IUPAC prefix for 3 carbon, that is propane, so propanoic acid. But if you look at the common name, it is pronounced similarly, but the spell that is to be written here is different. It is propanoic acid rather than propanoic acid. After that we have butanoic acid, and the corresponding common name is butyric acid. Then further we have this the 2-methyl. So if you see the structure, if you span the structure of this thing, it would look like this. CH3 C CH3 H COOH. So this one will be the longest chain, or you can take this one also, but both of these are of identical length, so we can take either of them. Now at the second position, so first and second, at second position we have the methyl group. So 2-methyl for the second substituent, that is the methyl group, propanoic acid. The next group member is, this is a dicarboxylic acid, as it has 2 carboxylic acid in it. Now the name is oxalic acid. So if you have heard this term, I think you must have heard it. This is called oxalate ion, and it is the most popular form, or you can say the common form of this oxalic acid. Next we have the malonic acid. So difference is that we have introduced one more CH2 group, or the methyl group, in between these two carboxylic acid group functional groups. Clear? That would be termed as malonic acid. If we introduce one more carbon, it will be succinic. 3 more carbons, glutaric. 4 more carbons, adipic acid. Clear? Now one more thing here. So if you have 3 carboxylic acid, and the structure of this, try to draw the structure of this by yourself. So we have 1 carboxylic acid here. 1 carboxylic acid is attached to the third carbon, this one here, and the third one is this one. So we have a total of 3 carboxylic acids. So tri-carbolic acid, or simply it is called as carbolic acid. Now if you look at the corresponding nomenclature, so 3 carbons, so propane dioic for 2 carboxylic acid. Then again we have 2 carboxylic acid but 4 carbons, so butane dioic acid. Then pentane dioic acid. Okay. Further we have hexane dioic acid for 6 carbons, 4 carbons in this bracket, and 2 on the carboxylic acid, so hexane dioic. Then we can have propane 1,2,3 tricarboxylic acid. So why is it named so? So for that, let us look at the structure once again. So what it is written? It is written as propane 1,2,3 tricarboxylic acid, and the structure is in this way. So we have 1C here, 1C here, and 1C here. 1H is placed here like this. 1 is placed here, and 1 is placed here. Now let us satisfy the remaining valency with H. Okay. So this is the group. Now if you name it, if you just name it, so let us start from this side. Why am I starting from this side? Because it doesn't matter in any way. You can start from either side, that would result in the same name, because 3 of these carbons are already preoccupied by the carboxylic group. So the first, let us consider the first carbon at the left one, the second, third. Let me write with a different pen so that it would be more clear. So first, second, third. Now at 1 we have the carboxylic acid, with 2 we have carboxylic acid, and 3, all of the 3 positions are occupied. So for 3 carbons we have the name propane, or suffix propane, prefix propane I would say, and 1, 2, 3 tricarboxylic acid. So propane 1, 2, 3 tricarboxylic acid. So we have just introduced the suffix against this carboxylic acid. So for 2 we have dioic acid, but for 3 we have to write it the whole way, tricarboxylic acid. After that we call this one as benzenoic acid. Likewise we call this aldehyde. So suppose it was, if it were aldehyde, then what would we call it? So if it would have been aldehyde, CHO, then we would call it benzaldehyde. Okay. Or if you look at the IUPAC name, then it is benzene carboxylic acid. Now this benzenoic acid is also considered as the IUPAC name only. Next we have phenyl acetic acid. Why is it phenyl acetic acid? So this group here is called as phenyl, and I have told you that if the carboxylic acid is attached to 1 carbon only, then it is called as acetic acid. So phenyl acetic acid. Or if you want to write the IUPAC nomenclature, so At first position we have the acid. So first carbon is at the acid. At the second position we have the phenyl. So 2-phenyl ethanoic acid. 2 carbons, so ethanoic acid, and phenyl for this whole group. Now you would say, sir, that you have told that okay, you have to consider the carbon also when we are counting the functional group, or you can say by counting the chain length. So you have not counted this 1, 2, 3, 4, 5, 6, 7, 8 carbons are there. So it should be oct, or it should be oct. So this prefix should be oct. But students, this is not applicable for methyl, phenyl, or any alkyl chain. It is only applicable in case of heteroatom chain, like your carboxylic acid, or say we have this ketone or aldehyde. So in that case only the carbon of that functional group is counted. But if we have a simple alkyl chain, then we name that alkyl chain separately. It would not be included along with the name of the carboxylic acid or any functional group. Then this is called as phthalic acid. We have 2 consecutive carboxylic acid on 2 positions, or we can call it benzene 1,2 dicarboxylic acid. Suppose it is 1, then it would be 2. So benzene 1,2 dicarboxylic acid. Okay, clear? So these are the name of some carboxylic acid. Next, let us move to the structure of carboxylic acid. So if you look at the structure of carboxylic acid, so this is the structure of carboxylic acid. We can have an R group here. Now this structure is planar in nature. What does it mean? It means that all the substituents of this carbon I am talking about, all the substituents of this carbon, not the adjacent one, only I am talking about this carbon. The substituent that is directly attached to this carbon are on the same plane. Whether you talk about this oxygen or this alkyl group, that can be carbon, CH3 suppose. So all the substituents that are directly attached to this carbon of the carboxylic group are on the same plane. And if the conditions are ideal, then we will get a 120-degree bond angle between the 2 bonds. Okay. Now this carbonyl center. So we have seen carbonyl center earlier also in case of your ketone or aldehyde. And in that case, we have seen that it can undergo your nucleophilic substitution or addition. But the case for carboxylic acid is different. It is not similar to those two, that is aldehyde or ketone. And what is the reason? The reason is the resonance structure that can be formed by the delocalization of this lone pairs. Okay, so this lone pair are delocalized in the along the 3 atoms, that is oxygen, carbon, and oxygen. Now as the this lone pair are delocalized, this decreases the polarity of the carbon oxygen bond. Okay, and you know that the polarity of this bond is very important for the facilitation of the attack of the nucleophilic attack of the nucleophile. So if I would say, then in steps I would say that first the delocalization of electron takes place. This increases the negative charge on carbon because this electron is donating this oxygen is donating electron in the carbon orbital. Then further it decreases the polarity because the negative charge is neutralizing the delta positive charge that has been created by the electronegative oxygen, and this decreases the reactivity towards carbonyl center. Okay, so this is about the structure of carboxylic group. Now when you will study the reactivity of carboxylic group, you will be able to develop a bridge or a sense between the structure and the reactivity. Why is it less? Okay, coming to the reactions of the carboxylic acid, first we will start with the reaction of the preparation of carboxylic acid. First we will start from the preparation that takes place from alcohol and aldehyde. So we can do it with the help of aldehyde also or alcohol also. So how do we do it? So for that, what are we doing here? First of all, now let us try to procrastinate the situation that we are looking for. So we are looking at a group that is your alcohol. So what is the structure of alcohol? So in alcohol we have a carbon. In alcohol we have a carbon. So in alcohol we have a carbon. Okay, in alcohol we have a carbon here, and that carbon, this carbon has been directly attached to 2 H groups, 1 oxygen and 1 R group. Okay, so they are attached. Now what will happen? What we have to do? We have to change this to carboxylic acid. That is, we have to add oxygen. We are adding 1 oxygen. So to add oxygen, we have to oxidize it. I would say in simpler terms that we have to oxidize it. So how you would oxidize it? With the help of oxidizing agent. So there are multiple oxidizing agents that can be used to do this thing. Okay, so what are the oxidizing agent? So I have shown two types. First one is the KMnO4, that is potassium permanganate, and the second one is Ki2C27 and CrO3. So this is called as Jones reagent. So this is a very strong reducing agent. So if you have a primary alcohol, say you have a primary alcohol, the Jones reagent will directly convert, I would not say directly, but it converts it into carboxylic acid via diol. We'll see the mechanism which is given here. So it converts this primary alcohol to carboxylic acid via diol formation. You can do it with the help of KMnO4 also, as I have told, and with the help of Jones reagent also. Now, what happens if we are an aldehyde? We can do the same thing. No problem. We can do the same thing. So we will talk about this aldehyde only right now, that how can we convert your aldehyde into carboxylic acid with the help of Jones reagent. We can also use the same method for the preparation of this aldehyde from your alcohol. How it is done? So if you look at the structure of CrO3, it looks like this. So if you treat it with H2SO4 and H2O, that it results in this kind of structure. It is a chromium complex having double bonded oxygen, two double bonded oxygen and two hydroxy group. Now it has empty orbital, empty d orbital. This chromium has empty d orbital. So suppose we have started from aldehyde. Say we have started from aldehyde. If you treat your aldehyde with H2O, then there is a chance that certain fraction of the molecule will be converted into this diol. Now, as soon as it is converted into diol, what will happen? This O that is present here, it will attack the chromium center which is having empty d orbital, or it, in other words, I would say that it will donate its electron to the chromium d orbital. This would result in this kind of complex. Okay, this would result in this kind of complex. Now further, this bond will move here. Okay, this bond will move here, and this chromium H2CrO3 will be kicked out. So let me do it for you how it is done. Okay, so first of all, we have this thing, that is okay, and we have our carbonyl which is being converted into diol. Suppose we have two groups on both sides, R and R dash, no problem. Now the lone pair on oxygen will attack this thing. It will attack here. Now in the next step, what will happen? This pi bond will go here. This pi bond will go here and it will revert. It will go here. First of all, it will go here and it will revert back and kick out this OH. So, and how this leaving group removal is facilitated? It is facilitated due to the presence of acid. So the acid say protonate this oxygen and make it a good leaving group. You can also imagine it in this way, that this oxygen is attacking here and the H plus that is being present on O is being transferred to this OH. So this would result in this kind of intermediate. We have OH here, we have R here, we have H here. Okay, we have this thing, these things here. So we have to take R here. Why? Because we have taken aldehyde, started from aldehyde. Now this H plus will be removed in this fashion. Okay, it will be removed in this fashion. Clear? And it would, and this would fall and result into your carboxylic acid. We have an OH here and a double bond O formation is taking place here. Now what happens if we take alcohol in place of this? Just try to do it by yourself. You do not have to worry about it. It is very simple. So if it would have been alcohol, and that also primary alcohol, then what would it contain? It would contain H here first of all. The attack would have been same. Now in the next step, we have H here. Now one of the H will be removed, and that would result in the formation of your aldehyde. That is given here, RCHO. So this is the preparation of your carboxylic acid from your alcohol or aldehyde. So one more reagent is there, that is KMnO4. So I'm not giving the mechanism here. It is quite complicated to follow, but it goes through a concerted mechanism. So if you are curious about this, you can work on it. It goes through, first of all, I'm giving some clues. It goes through this concerted mechanism, and MnO4 looks like this. Clear? So this is the preparation of your carboxylic acid from alcohols and aldehyde. Now let us next move to alkyl benzene. So this is a very interesting reaction. Why it is interesting reaction? First of all, for the starting of this reaction, you must be very careful about the terminology, that is alkyl benzene. So this is alkyl benzene. This is also alkyl benzene. This alkyl is attached to this benzene. Okay, so these both are alkyl benzene. Now this alkyl benzene can be of any length. So what do? We treat this alkyl benzene with KMnO4 and KOH in the presence of heat, which gives us carboxylic acid directly. And no matter whatever be the length of the chain, all of this will be removed and we'll be left with the carboxylate ion. Now in this case, you have to heat it harder because it has a carbon-carbon bond and it has to be broken and removed to get this thing here. Now at last we do the permutation. Now what is this reaction peculiar about? It is that primary and secondary alkyl groups are oxidized in this manner. You cannot do this with the help of tertiary alkyl group. So suppose the functional group looks like this, or the substrate looks like this. Then this would not be oxidized to a carboxylic acid. Okay, only secondary and primary, two types of alkyl groups can be converted into carboxylic acid. Now suitably substituted alkenes are also oxidized to carboxylic acid with these oxidizing reagents. So we will see those suitably substituted alkenes in the next class. But for now, assume that alkenes can also be oxidized to your carboxylic acid. If there is an alkene in here, then it would have been also oxidized to your carboxylate ion and further protonated to form your carboxylic acid. Okay, clear? So far we have seen two preparatory methods from alcohols and aldehydes in both, and from alkyl benzene, and in all of this we have used strong oxidizing agent. So we are oxidizing these two things. Now next, let us move to what we can do in case of nitriles and amides. So here is our nitrile. So this is nitrile. How does nitrile looks like? This is nitrile. Okay. So first of all, we treat this nitrite with this H plus or OH minus in presence of H2O. Sorry, we treat with this nitrile with H2O in presence of acid or base. So how this reaction will go? So we have a nitrile group here, like this. Now in the next step, what will happen? We have a H2O. This will attack here. Now as soon as it attacks here, the proton transfer takes place from hydrogen to oxygen to nitrogen and result in this kind of entity. Okay, so it would result in this kind of entity. Now next, what will happen? So we have to form CONH2. Now again an interproton transfer takes place. So this bond comes here and this oxygen, sorry, this hydrogen is transported onto this nitrogen to form at last CONH2. And this is called amide. So if you do the acid and base hydrolysis of your nitrile, then it would result in the formation of amide. Now on further hydrolysis, but in the presence of heat, would result in carboxylic acid. Now you can take different type of amides. Suppose we have taken ethanamides, then if you treat it with H2O and hydrolyze it in the presence of H plus and heat, then that would result in ethanoic acid plus NH3. Again, if we have benzyamide similar to benzoic acid or benzaldehyde, we have benzyamide also. So if we treat our benzyamide with water and acid in the presence of heat, then it would also result in the formation of benzoic acid and NH3. So we can make a general statement that, okay, if we have nitrile or amide, we can hydrolyze them in the presence of a H plus or OH minus and heat it further to get our carboxylic acid. Okay, so this is our preparation from nitriles and amides. Now let us look at the mechanism here. So we have a 3-step mechanism that has to be followed for the formation of your carboxylic acid using amide. So our amide is here. If I look at the first step, the first step is protonation. What is the first step? It is protonation. So we have amide here, we have oxygen here, so we have H2 also, H3O plus, as we have introduced it in the presence of acid. We are taking the acid part. You can try it with the base thing also. So first of all, suppose the acid is HCl. So this H plus will be transferred on to oxygen and it will create OH plus and Cl minus, the counter ion of the HCl. Counter anion of the HCl, I would say. Now this has, again, we can see that oxygen has a positive charge. Now I have mentioned it earlier that if we have a positive charge on oxygen, then that would increase the nucleophilicity of this center. This thing is again observed here also. Now what is the reagent that can do this? We have water, since we are hydrolyzing it. So hydrolysis means means reaction with water, clearly. Or it can be acid or base catalyzed, that is a different matter to be discussed. But if we talk about hydrolysis, then it is simply reaction with water. Okay, so here we are with a nucleophilic center and a nucleophile, that is H2O. Now the lone pair that is present on oxygen will attack this center and create a OH2 plus. Okay, so this will create a OH2 plus because now oxygen has one less electron, it has shared it to carbon, and this pi bond will be shifted onto oxygen. So that would result in this kind of intermediate. Now you must have seen this intermediate. So if you just deprotonate the H2O plus, why? Because it is an acid catalyzed reaction, so it will be reverted back. So this H plus will be removed and we are left with the diol. Now what will happen? This diol that is present here, it will again take the H plus. Okay, so let me do it for you. The last step is not very clear, so I will do it for you. So we have one OH, we have again one OH, and we have NH2. Now H2O is being protonated due to the presence of acid, and it is H3O plus. So this will be taken by NH2. So what would it result in? It will result in a diol and a NH3 plus attached to it. Okay. Now this lone pair on oxygen will push this thing because it is a good leaving group, so it will leave here. So this would be the end result of this mechanistic part. Now we have again oxygen, protonated oxygen. So since it is acid catalyzed, initially it has donated one hydrogen, so it will be taken up back, and that would result in your carboxylic acid. So this is our mechanistic part of the hydrolysis of amide. Now we can do the same thing with esters also. So if we take esters, we can do the same thing. So how it is done? Now let us take the mechanism of ester. So here are some examples. We have taken ethyl benzoate, we have treated it with H2O and H+. So we get benzoic acid. Again, we have hydrolyzed this thing and we got this one. Now why is this C2H5 not going to COOH, C2H5 COOH, and why is this group only going to this thing? So we look at the mechanism for that. So this is ester. So ester basically looks like this. If you don't know, ester looks like this. It is just a derivative of your carboxylic acid, only the H has been removed with another alkyl chain. Let us first start with this base catalyzed reaction. So now first of all, let us look at the point that ester are hydrolyzed to carboxylic acid. That would be in the presence of acid and base both. Now one more important point here, that we can similarly hydrolyze acyl halides and nitrates also. So acyl halides look like this. So I have mentioned this structure earlier also, and I'm mentioning it again. So this is acyl halide or anhydrides. No problem. Okay, now let us start with the ester hydrolysis first of all. So first of all, let us begin with this base catalyze. So for base catalyze, we have OH minus. Now what will happen? This OH minus will attack here on the nucleophilic center. This pi bond with the carbon and oxygen will go to oxygen and resonate back to kick out this OR2 back group minus, sorry, R2O group minus. So it is a very important thing to notice here that this is a very good leaving group. So it will be kicked out. Now this R2O minus will take one H from here, and that would result in this thing. Now you would say that why is it so? Why have done this step? This is very important. Okay, this is very important to mention this step, because now students, tell me what will happen. What will happen if we are using OD minus in place of OH minus and H2O? Now this OD minus will attack here. Okay, no problem. OD minus will attack here and it will be kicked out. Now this, where will be the D present? This D will be present with this carboxylic acid or with this alcohol. For that you have to well aware about this part, this mechanistic part. You would say that, okay, since I have protonated this one, so this would get protonated at the first site. But no, this is a stronger acid than this thing, or this is a stronger base than this acid. So this base will take one H plus from this acid and will result in R2OH. Now since we have used OD minus here, so therefore this R2OH will be converted into R2OD. So this is the base catalyzed hydrolysis of your ester. Now what will happen if we take the acid hydrolyze? So this is the example of acid hydrolyze esters to form the carboxylic acid. So we have acid. Acid is always present as H3O plus. You can take H plus also in this place. No problem. You can do this. But if you talk about the appropriate mechanism, then I would say that you should include H3O plus rather than H plus every time. Every time there is aqueous solution of acid, take H3O plus rather than H plus. Okay. Now again, this O that is present in ester as lone pair, it will take your hydrogen from the protonated water. That would result in this kind of intermediate, and the attack is facilitated by water. So this water will attack on this center, and the pi bond between carbon and oxygen will move upward to form this kind of structure. Okay, clear? Now next what will happen? So since this O has been now positively charged due to donation of electron from oxygen, so this H plus has to be removed. This H plus has to be removed. So this H plus is further removed by your, say, ROH group. So you can see that a proton transfer has been taken place. So there are two R group attached. So one R2 is attached with O and one R1 is attached to carbon. Now this oxygen will take this H, and further this OH that is present here. So diol is present here now. This is diol. Diol means two hydroxy group on the same carbon center. Now this double bond between oxygen and the single bond between oxygen and hydrogen will be clipped due to the extraction of proton by H2O from O. So this will be removed and this R2OH will be kicked out. Okay, so this is the overall acid catalyzed reaction. So what do we say now? That okay, our ester can be hydrolyzed to your carboxylic acid both with the help of base and acid. Okay, clear? Now next, let us move to reaction with Grignard reagent. So this reaction is very interesting to follow. So what do? We are taking a carbon dioxide here and we are treating with RMGX. Now just try to first of all do it by yourself. That okay, we have taken one carboxylic acid, sorry, carbon dioxide. So at first sight, it would appear to you that what will happen? This is a inorganic molecule. This is CO2. This is the organic molecule. What it is doing with this thing? So although this thing is inorganic, but the main point to here notice is that this carbon here is a nucleophilic vulnerable spot, and this is a very good electrophile. This is a very good nucleophile because this R has a negative charge as it is attached to a metal which is having a positive charge. Now this R minus will attack on this center. It will attack on this center and the double bond will go on this oxygen to create this thing. So let me show it to you. It happens in this fashion. We have a CO2. We have RMGX. First of all, this lone pair will chelate with your MgX. So it will look like this now. Okay, CO2. Now I have told that there is a chelation between Mg R and X. No problem. Now this R group, this will attack on this center. Why? Since this has this oxygen has donated it electron, or you can say there is an interaction between the electrons of this oxygen and magnesium, there is a development of partial positive charge, and as soon as this partial positive charge is being induced on this oxygen, it can be facilitated. Sorry, this nucleophilic substitution can be facilitated. So this R attacks here, and we get O minus. So it will move here. This pi bond will move here, O minus and MgX plus. Okay. So the same thing is written here also. O minus and MgX plus. Now you can further protonate it. You can further protonate it with H3O plus to get our carboxylic acid. Okay. Clear? So this is the reaction with Grignard reagent. Students, one more thing. I have told you in the previous slide that you can hydrolyze this, say our anhydride, or we can have this acyl halide to give the carboxylic acid. So I am doing the hydrolysis of one of these, that is your anhydride, and you can try the hydrolysis of RCOCl. So let us do it. So suppose I am doing your acid catalyzed hydrolysis. So what will happen? So first of all, this thing will be protonated in the presence of H plus. So it will result in the formation of OH plus. Okay, and R dash. Now we have H2O in water. Suppose this H2O is H plus is given by H3O plus. Now we are left with H2O. Now this H2O, oxygen has lone pair, it will again attack here. So we have a positive charge on oxygen first of all. We have R dash here, and we have OH here. Now an interproton transfer will take place and H will go here. Okay, so we have an OH here and we have a OHR dash here with a positive sign. Now what will happen? This will move here and kick out this group with a positive sign. So that would result in 2 moles of carboxylic acid. Okay, so acid anhydride can be hydrolyzed in the presence of acid or base to give 2 moles of carboxylic acid. So far in this lecture, we have seen various methods of preparation for the carboxylic acid. So we have basically started first of all with the nomenclature. We have seen some important carboxylic acid. So those were what? I would say that we have seen initially some important carboxylic acid. I would mention some of them. So I would say that this is important. This is called phthalic acid. Okay. This is called phthalic acid. Also, we have seen some di-tricarboxylic acid, like the one was adipic. So we have H here, COOH, COOH, H here, COOH. Okay, sorry. OH, COO, and OH, COO. So this is tricarboxylic acid. It is also termed as adipic acid. Then we have seen succinic acid also, oxalic acid also. So oxalic acid looks like this. Oxalic acid. Then we have succinic acid. Now you must be aware about each of this say common name about the acid because they're important. Okay, clear? So this was all about the nomenclature, and then we have seen methods of preparation starting from the oxidation of your alcohol and aldehyde, moving on to hydrolysis of ester, amides, acyl halides, or we will talk about this amides. So all of them can be hydrolyzed to your carboxylic acid. Okay, clear? So this was for today's lecture. So with this, I would end my lecture. Thank you. If you talk about tomorrow, we will see the reactivity of carboxylic acid. Okay. Okay. Thank you.